So in this short video, we can look at trends in electronegativity along and down the periodic table, but also look at what non-polar molecule is and what a polar molecule is and what it's got to do with electronegativity. Well, first of all, what is electronegativity? Well, electronegativity is the ability of an atom, or the tendency of an atom, to attract a shared pair of electrons. So you can see that atom B has a higher electronegativity, so it's able to attract that bonding pair of electrons more than atom A, and therefore they move closer to the atom B's nucleus compared to the atom's A nucleus. So if we have a look at the periodic table, so these numbers here are the electronegativity numbers. And you can see, first of all, that as you go along a period, those numbers increase. So you can see here you've got 1, 1.6, all the way up to 4. And if you go down a group, then the number decreases. So the electronegativity, the tendency to be able to attract a shared pair of electrons, goes down. And to have a look, the lowest electronegativity is down here, and the highest is fluorine up here. You'll notice that these are the inert gases which have a full outer shell already, so they don't react with anything, so they don't have any electronegativity at all. So if we first of all look at simple covalent molecules, and we're looking at elements first. So if I take nitrogen, for instance, a nitrogen molecule, you'll notice the electronegativity, if it is an element, is the same for both atoms. So they will share the electrons equally, and they will be exactly in the middle. So we've got 3 shared pair of electrons for nitrogen because it makes a triple bond, so that is nitrogen. If, for instance, we take fluorine, fluorine only needs to share 1 electron, and because they've both got identical electronegativities, because they're the same atom, they share that electron pair equally and is in the center. So let's have a look at what happens when we have significant differences between the electronegativity of 3. So chlorine has got a much better ability to attract that shared pair of electrons. So what will happen, first of all, is we know that hydrogen and chlorine share 1 electron each. But if we draw it like this, you can see the shared pair of electrons is much closer to the chlorine nucleus than it is to the hydrogen nucleus, because it's pulled that way. And so this makes the electron density, where you're going to find the electrons, much more towards the chlorine side. So what we can do, we can draw the polar molecule looking like this, where it gets fatter, there is a higher electron density. So although the molecule is still uncharged, because the electrons, those pair of electrons, move this way, this end has a positive charge to it, and this end has a negative charge to it. And so this is called a polar molecule. It has a positive pole and a negative pole. And we draw that funny symbol there to represent, and we draw a funny symbol there to represent the distribution of charges. So this end is more negative, that end is more positive. We can also draw it like this, where we've got the hydrogen here, we've got the chlorine there, and when you draw your covalent bond like this, you put a cross there to show that the shared pair of electrons is more towards the chlorine. So let's now look at a water molecule. So hydrogen has electronegativity of 2.1. You can see the oxygen's right over here. It'll have a much higher electronegativity, so we'll attract the shared pair of electrons towards its nucleus instead. So if we are drawing that, it will look something like this. We've got the oxygen there, we've got the hydrogen here, and both of the shared pair of electrons will be much more towards the oxygen than the hydrogen. So this again makes this a polar molecule, where this end, because the electrons are drawn here, will be negative, and these parts where the electrons are drawn away from, further away, will be positive. Overall, it is still neutral. And we can draw that like this. We've got the hydrogen and the oxygen. We've got our covalent bonds, but we put a little cross there to show that that shared pair of electrons is much more towards the oxygen than it is the hydrogen. And again, we can just put our positive and negative charges on. So I forgot those there. So those are non-polar molecules, and these are the polar molecules. So now let's have a look at explaining the trends in electronegativity as we go along the period and down a group. So first of all, we know that the electronegativity increases as you go along a period. And this is because the electrostatic attraction between the valence electrons and the nucleus becomes stronger. And this is for two reasons. Firstly, as you go along a period, remember, the proton number goes up. We have one more proton in the nucleus, which makes the nucleus more positively charged. And secondly, as we go along the period, the atomic radius reduces as valence electrons are attracted more towards the nucleus and the radius shrinks. So how would we answer this in an exam question? We would write electronegativity increases along a period as the electrostatic attraction between the positive nucleus and the negative valence electrons increases because the number of protons increases, and just remind yourself that there's the same amount of electron shielding because the shells are the same. And secondly, the atomic radius decreases. So secondly, as we go down the group, the electronegativity decreases. But why? Well, we know that if the electronegativity decreases, then the attraction of the valence electrons to nucleus reduces. And that's because of two reasons. Firstly, as you go down the group, we have an extra shell in each period, which means the atomic radius is increasing and the valence electrons are getting further away from the nucleus. But also, with each increased inner shell, we've got more electron shielding. So in an exam question, we could write electronegativity decreases because the electrostatic attraction between positive nucleus and negative valence electrons decreases because, first of all, the atomic radius increases, there are more electron shells, and secondly, a greater electron shielding. And that is a classic question in applied science for describing the patterns in electronegativity for the periodic table.